Every gas turbine, every steam turbine, every nuclear plant spinning right now is doing something for the grid that has nothing to do with generating electricity. It's invisible. It's not measured in megawatts. And as these plants retire, we've been treating it as free. It isn't. In 2023, the United States retired roughly 9 gigawatts of coal capacity. In 2024, another 7.5. Natural gas plants are coming next, hundreds of aging units reaching the end of their economic life. The solar farms and wind turbines replacing them generate the same electrons. But they don't replace what those spinning machines were providing on the side. NERC flagged this in their long-term reliability assessment. FERC issued a major order about it in October 2023. Australia already ran the version of this experiment that the US is now running. They learned something painful. Here's what a retiring gas plant actually provides, what the grid loses when it goes, and what the industry is slowly doing about it. A 500 megawatt gas turbine generator weighs hundreds of tons. It spins at exactly 3,600 rotations per minute, 60 rotations per second, locked to the 60 Hz frequency of the US grid. That spinning mass stores an enormous amount of kinetic energy, not in a battery, not in a capacitor, just in the rotation. Engineers call this inertia. When something goes wrong on the grid, a generator trips, a large load suddenly disconnects. The grid frequency starts to change. Instantly, there's now either too much or too little generation for the load. In a grid full of spinning machines, all that kinetic energy in all those rotors buffers the frequency. It changes, but slowly. The inertia buys time. Engineers measure this with something called the inertia constant, labeled H, in seconds. H represents how long the stored kinetic energy in a generator could supply its rated output if the mechanical input suddenly stopped. A large coal or gas unit, 4 to 8 seconds. A hydro unit, 2 to 4 seconds. A solar farm, 0. A wind turbine, near 0 unless special controls are added. The rate at which frequency changes after a disturbance is called ROCOF, rate of change of frequency. In a high inertia system, ROCOF might be negative 0.1 Hz per second after a large generation trip. In a low inertia system, the same event produces negative 0.5 Hz per second or worse. That difference doesn't sound like much. In practice, it's the difference between a controlled response and a cascade. Here's why. Generators have protective relays. Those relays watch for abnormal conditions, including fast frequency changes. If frequency is changing too fast, the relay assumes the generator has lost its connection to the main grid. It assumes the generator is running uncontrolled, alone, in an island. So it trips the unit offline. This is called a nuisance trip. In a low inertia system, an event causes fast ROCOF, which causes nuisance trips on other generators, which removes more generation, which accelerates the frequency drop, which triggers more trips. The cascade feeds itself. South Australia saw this in September 2016. A severe storm tripped several wind farms. The ROCOF was faster than some relay settings had anticipated. The remaining generation couldn't hold frequency. The entire state went dark, 1.7 million people lost power. The Australian energy market operator spent the next several years developing formal minimum inertia requirements for each region of their grid. The US has not done that yet. Inertia is the first thing a retiring gas plant takes with it. Fault current is the second. When there's a short circuit on the transmission system, a line falls, insulation fails, lightning strikes, voltage collapses at that point. Synchronous generators respond immediately. They push current into the fault, 5 to 10 times their normal rated output, for a fraction of a second. This sounds like a problem. It's actually how protection systems work. Protective relays measure current. High current means fault. The relay operates the circuit breaker. The faulted section is isolated in under a second. The rest of the grid continues. Solar inverters and wind converters are different. They're built with power electronics that protect themselves by limiting fault current. typically to 1.0 to 1.2 times their rated output. The protective relay sees a much smaller signal. Detection is harder. In some configurations, the relay may not detect the fault reliably at all. Every utility's protection engineers are re-examining their relay settings as the generation mix changes. In regions with high inverter penetration, this is one of the most active areas of engineering work happening in the industry right now. It doesn't make the news. It's the work that prevents the news. Reactive power is the third thing. Synchronous generators naturally absorb or produce reactive power based on their field excitation, automatically, continuously, as voltage conditions across the system change. This is what keeps voltage stable across hundreds of miles of transmission. Inverter-based resources can provide reactive power, but it requires deliberate design and deliberate control. It doesn't happen by default, and it trades off against real power output. You can't always fully maximize both at once. In October 2023, FERC issued Order 901, directing NERC to develop a comprehensive set of reliability standards for inverter-based resources over 3 years. The requirements cover ride-through performance. Inverter-based resources must stay connected during voltage and frequency disturbances rather than disconnecting. Data and model validation. Utilities must demonstrate how their inverters actually behave in abnormal conditions, which many currently cannot. And planning standards. Interconnection studies must account for IBR characteristics, not just assume they behave like the synchronous machines they're replacing. The deadline for the planning standards is November 2026. Full implementation, January 2030. Separately, a technology called grid-forming inverters is being developed and slowly deployed. A conventional inverter follows the grid's voltage wave. It's a follower. A grid-forming inverter can synthesize the voltage wave itself. It can produce something that behaves like inertia. Hornsdale Power Reserve in South Australia, a large grid-scale battery, was one of the first real-world tests at scale. The results were good enough that Australia now requires grid-forming capability in new large-scale battery installations. The US does not have that requirement. Here's the loop. Every gas turbine retiring right now is taking something with it. Not just megawatts. Megawatts are replaceable. Solar and wind generate megawatts at scale. What's harder to replace is the physics. The inertia stored in spinning metal. The fault current that makes protection relays operate in under a second. The reactive power that stabilizes voltage automatically as conditions change. These weren't services anyone formally designed and paid for. They were side effects of machines built to do something else. And now that the machines are going away, we're finding out what those side effects were actually worth. FERC's deadline for the IBR planning standards is November 2026. Full implementation is January 2030. Every new solar project interconnecting between now and then connects under rules that were written for a different grid. NERC tracks inertia trends across the interconnections. ERCOT monitors system inertia in real time. The Australian grid operator publishes minimum inertia thresholds by region. What the US minimum should be. How much inertia the eastern or western interconnection needs to stay stable has not been officially determined. The math isn't done.